All right, guys, I don't know how this video is going to play out right now, but I'm going to tell you that I'm going to work on the cylinder covers. That's what they're called on the plans. And this is the cylinder head, and this is the transition bushing or the transition plug, slug, whatever you want to call it, that goes between the standard and the cylinder on the top. So some degree of precision and concentricity between all these features is very important. The 5/8 diameter that's called out here is intended to slip nicely inside the 5/8 diameter in the standard. So make sure you control those as such. The 3/4 diameter on top fits into the 3/4 diameter bore here, and the concentricity and precision of that fit to this hole is a little more important than the concentricity and precision of this 3/4 to that, because this is strictly a cap. That's the head. The upper detail, well, make it whatever you want, because this is really arbitrary. It means nothing. Starting off with 35 millimeter metric stock. I think you all know how I feel about metric material. Anyway, 1 3/8 diameter. This is supposed to be the tangent diameter for the cylinder, but I know that my cylinders are 1 3/30. This has probably got the overlap, so if you put the skin on there, it overlaps the skin or the shielding, and everything looks wonderful. Well, I haven't decided whether or not I'm going to do that, so I will probably start with the 1 3/8 on the print, and if I don't like it, well, I'll just pressure turn this down to the 1 3/30 so it matches and everybody's happy. Though it's not shown, it does get the same bolt pattern here. There is no clocking involved, so it really doesn't matter where the holes are in relation to this, so long as that when you turn the part, all the holes line up. That's it. That's the only thing that's important. Going to start with this guy here. I'm going to approach it from this side in the lathe, so I can do the through hole, the threads, the primary standard diameter, the OD dust, and then I will come back in here and I will just gently dust that off with the parting tool so that I have a parallel surface, so that when I flip it around and do the back side, I have something to indicate on to know that the part is square. So that's the philosophy behind that part. Let's just put this material in the machine. Hope I don't break out a huge rash because I touched it, and get something going. Five 5/16 26 on the print. Going to the Bible of all Bibles, the book, Machinery's Handbook. Goes from 24 to 27. Surprise, surprise. There is no 5/16 26 in the book. Well, that is not a problem. As far as I'm concerned, it is a fantastic opportunity for a refresher. So let's do that real quick, because I got to know too, right? Five 5/16 26 TPI. Threads per inch. 5/16 decimal equivalent. 0.3125. 3125. That is just a little bit bigger than 7.9 millimeters. Or what? Come on, Joseph. Wow. 7.9. 7.9 millimeters. There we go. Now, how do we figure out what the tap drill is for this? Well, we take this and we divide that into 1 inch. So one inch divided by 26. A whole lot easier to do that on a calculator. 1 divided by 26. Boom. 0.38 for per pitch. That is crest to crest, root to root, pitch to pitch, whatever. 26 threads per inch. Each thread is 0.38 That is almost 1 millimeter. Almost 1 millimeter. Not quite. Missed it by that much. That much. All right. Now we're going to take the 312 and we're going to subtract this. 0.3125 minus 0.0384 equals 274.1. Let's see what that is in metric. For what it's worth, 7 millimeters will do the trick. And in true metric form, let's just say, just for yucks, if this was an 8 millimeter by 1 thread, you would take the size of the screw, subtract the pitch, and that gives you the drill. Major diameter, pitch, tap diameter, tap drill diameter. Okay, 274 tap drill for what I'm about to do, and that is good to have. I will put that on the print. Take a mental picture of that. There's nothing wrong with your eyes. The paper is not moving. Trust me. Or not. Okay, dimensional note. This is called out as a 156 to 156.5 hole on the print. I measured the material. The material is 157, 157 and a half. I'm going to go with a 2/1000 oversized because I want this rod to ride on the Teflon or the graphite wrapping inside the compression area. So I'm going 2/1000 over on that hole right there. And this is cast iron material. I thought it would be a low lead cold roll like the PM research kits, but it is not. It is cast iron. And with that in mind, the 159 is the call. Without having moved the cross slide on the setting that I finished this diameter with, I'm going to record that setting, and when I face this off to the final dimension from the face to the surface called out on the print, I'm going to exceed that finished diameter setting on the cross slide, so the tip of the tool leaves an undercut in that corner as I face it. This is a TPG insert. It's going to result in a 60-degree undercut right in that corner, about 10 thousandths deep. That should be ideal. see if we get a better look at that. Now, if everything went well, the standard should go right on there and flush right to this surface because of that undercut. I like it. Yeah, and for sake of consistency, try them both. Beauty. Next stop, plunge and undercut right here, so there's an indication diameter to mess around with when we flip this part around. I will hold this in a collet when I flip it around because it's a nominal size. Why not, right? Usually do this with a razor blade, but I know this scale is nice and straight, so scraping the face of the part, I'm looking for the interference of the parting tool and moving the carriage until the scale doesn't hit anything. That is now digital 0. Going to move into the required dimension plus 10 thousandths. Plunge down to the rough diameter, then I will move over again and part the piece off. Now that the parting tool is going to engage this piece off center, which off center of the tool itself, it's only going to be taking half a bite. The tool is going to have a tendency to want to do this. It's going to have a tendency to want to push away. So I'm going to apply gentle pressure to the side of the tool to make sure that doesn't happen. And before I roll on to the backside operation, this is what you got. Finish diameter here, finish diameter here, finish step, finish through hole, finish threads. Turn this around on the collet, indicate the back to make sure it's not running like this. As soon as it's running true, and I know this is true, I'll finish up the front diameter and the front step and the overall thickness. Then I'll drill the holes. And I'll make another one. The 4 pieces that we just made have one common feature, and that is the 750 boss on the bottom. That is the feature that I'm going to use to locate these to drill them, because they all get the same drill pattern, and you know, it's going to keep them concentric. And this is the fixture going to do all the work. Nested in there real nice, 5-hole pattern. And on the ones that are not brought to thickness yet, once I'm done drilling the holes in these, I can then hold on the flange and deck this off in the mill to bring this to the height. That's going to save me from doing soft jaws or special collet or whatever, because the grip surface on the back is just not conducive to a secure grip. It's only 31 thousandths of an inch. That's about 8/10 of a millimeter, somewhere thereabouts. I'm going to use a single clamp on this because I trust that it's going to hold. Going to hold it right down the center, and I'm going to split the 5-hole pattern, 2 holes on either side of the clamp, 2 up here and 1 in the front. So this one clamp should do the job all the way through. Let's find out if that's true. Next piece in line is the actual cylinder head. One side is a little bit bigger than the other, and I guess that's so you don't put it on backwards. Well, I don't see what difference it makes. With the exception of the projection here, you'd probably crash the piston. Drill hole pattern is going to be exactly the same, and I'm going to thin it down by clamping here like I mentioned before. So we'll fast forward through this rather quickly and then get right to the milling. The drilling operation is complete. It's time to deck the top surface down to the overall thickness required, and I may put it back in the lathe and chamfer that edge because I think the head would look much nicer if that were round or at least a generous chamfer. Let's mill this off and figure that out later. Let's pop it out, rub it on some emery, and figure out what we're going to do about that edge. I intend to break the edge on this part with a 45-degree tool and follow it up with a file. This is a pressure turn operation, just a 3/4 inch nest piece of material. And we're going to stick this guy in here like that. All right, let's take a look at the progress up till now. I'm just going to do one side on the bench because it's getting heavy, and without nuts on these studs, it's going to fall over. Well, the transition bushings that we just made. There you go here. Cylinder goes on top of that. Cylinder head goes on top of that. Just on the outside. Where are we at? working my way back down from the base of the cylinder. Next piece in line, number 8, the gland. Small brass component. Should be fun. Okay guys, the next operation is to put the through hole in that will guide the valve rod in and out of the steam chest. It has been pointed out in the past that a generous chamfer on the inside of this and a drill point remaining inside the steam chest is a good idea to help form the packing into a constrictive geometry. So I'm going to put a rather large center drill end feature on that, and that is why I'm doing that. There are 2 pieces on this blank. There's one of these glands on the other side. Since it's a 2-cylinder, I need 2 of these glands. I'm going to take it over to the mill, put the little serrations on the outside, bring it back, part it off, and then I'm going to use my little gauge that I made here as the arbor to face the back off. I had thought about making this a hex. A 433 is the largest hex you can make on a 1/2-inch diameter, but in the interest of metric affiliation here, I was going to make it a 394, 10 millimeters. But then I realized that the limited access you're going to have to this, back in the day, they probably used these notches with a spanner wrench or a punch, because this will be down inside the standard and very hard to access. So the notches are a better choice than a hex, and that's why I did it. Let's take it back over the lathe, part it off, finish it up. Well, here's what the parts look like when they come off of the second op on the lathe, and that was just strictly facing off the back. Maybe a little cleanup, we'll see. Now, I don't know if I set it in fast motion or not, but these little chamfers on the inside here direct the packing material into a compressed neck down, so it chokes the valve rod or the connecting rod that goes through here. There's one. This is the connecting rod fitting. And the steam chest fitting is done just about exactly the same way as I just showed you with these guys, but there's really no point in reliving that. You've already seen it once. The only difference is these are a little bit smaller, and they're a hex instead of a scallop because these are easily accessible on the outside of the steam chest. And the steam chest goes right there. And of course you got to do everything twice because it's a two-cylinder engine. This is the rod that will control the valve that will regulate the steam. I guess that's why it's called a steam chest, right? Well, there you go. I think for everything that was included in this video, I hope I didn't skip over too much or disappoint anybody with the way the work was presented. But I gotta say, that was an awful lot of work for apparently relatively insignificant parts. Hope you enjoyed what you see. I hope you come back for the next installment. We are checking parts off the list left and right, and I was really glad to get these guys done. It's exactly what I wanted to accomplish today. This is officially the end of this video. Thank you very much for tuning in, spending some of your time with me today. Wherever you are in the world, I hope you're well and happy and safe. All of the above. Me, I'm Joel Pye, Advanced Innovations in Austin, Texas. End of the day, it is beer 30 here in the USA. I'm out.